All right, welcome, ladies and gentlemen, to section 4.4. This is our introduction to graphing the trigonometric functions. And this first video, we're just going to solely focus on sine, the sine function, and we're going to have another separate video for each of the other 5 functions. So let's go ahead and just start looking at the sine function. So the parent function is obviously f of x equals sine of x. The domain of this function is all real numbers because I can plug any number I want into sine, either positive, negative, decimals, radicals, anything that I want, I can plug into the sine function. The range of the sine function, the parent function, is from -1 to 1. So it has a total height of 2, which actually means it's bounded because it doesn't go below -1 or above +1. And all sine functions will be bounded. And all sine functions will have a domain of all real numbers. It's the range is what starts to change as we look at more complicated functions. The period of the parent function is 2 pi. We're going to change that eventually, obviously, but right now the parent function is 2 pi. It has odd symmetry, which means it's a symmetric about the origin, so it will rotate around the origin 180 degrees. And here's what the graph is going to look like. So just by thinking about plugging in values, if I was to think about just plugging in the sine of 0, I know the sine of 0 is 0. And if I just look at the things that are on my graph here, I know the sine of pi is also 0, and the sine of 2 pi is again 0, and I can continue this in any direction. The sine of -pi and the sine of -2 pi is also 0. But here's where it makes a difference. Right in the middle is pi over 2. And right in the middle here is 3 pi over 2. You might remember that these 4 angles here, 5 including the 0, are our quadrantal angles. They're the ones that are on the quadrants of your circle. The sine of pi halves is +1. And the sine of 3 pi halves is -1. And this continues backwards. The sine of -pi halves is the same thing as 3 pi halves. And the sine of -3 pi halves is the same thing as pi halves. And as good as I can do, I'm going to connect the dots here on the computer. And it's going to come up here like this. Round off the top. Down. Rounds off here. And I'm doing the best I can to make sure I get a good line here. I do much better with a pencil and paper than I do with this computer. Now, this is the sine curve. Notice the domain. The arrows just continue forever. Okay? It never goes in the parent function. It never goes above +1 or below -1. All right? And I did go through the 2 pi here. So this is the graph, and I really focus on these 5 values right here. And I'm going to start off with the 5-point method on graphing. But what we're going to start off just here is I just notice that the sine function goes through the origin, goes through 0, 0, the parent function, and normally goes up, middle, down, and middle. We're going to use that later on in this video. So become familiar with the parent function of sine x. So let's look at what happens if we were to translate this function. So we call these things sinusoids. Both the sine and the cosine are called sinusoids. And what happens here is we start introducing the other values. The a, the b, the c, and the d. And we might be able to figure out what these things do just by using what we know about transformations. If we multiply by a number in the front of the function, we know that it changes the vertical stretch. We know that if we add a number to the outside of that, it moves the function up or down. And we know that if we multiply the x by a number, it does a horizontal stretch. And if we plug in a plus value or a minus value on the inside, it moves left or right. And it does just that. We just have new names for certain things. A, or the absolute value of A, represents the amplitude. And this determines the height of the graph. So in the parent function, A is 1, and that's why it goes up to positive 1 and down to negative 1. And we use absolute value here because if it's negative, it just flips the graph over. So we don't really care about the negative when we determine the amplitude. The B value is used to determine both the period and the phase shift. Phase shift to come later. Don't worry about that just a second. But right now we're going to use B to represent or to find the period of the sine function. And if you think about period being one full revolution, going from 0 to 2 pi, that B is meant to shrink or stretch horizontally, which actually is the period. The horizontal is the period here. So the period that we're going to be finding is 2 pi divided by B. Since the original period is 2 pi, we divide by that B value to determine the new period of the function. C, if there's a C term in your function, there is a phase shift, which is actually just a fancy name for a horizontal shift. And in order to find the phase shift, we use the value C divided by B. And I give you a little note here. Remember your transformations. If it's a plus C, as this picture shows up here at the top, if it's a plus C, it moves to the left. And if it's a minus C, then it moves to the right. And D is simply the vertical translation. And on the parent function, the center line of my graph is the x-axis. But the D is my new center line. I like to call it the center line. I actually put in a dashed line to represent where the center of my graph is at. And it's exactly as you remember from transformations. A plus goes up and a minus goes down. So let's look first at what I'm going to call the 5-point method. I don't know if the book calls it that or not, but I'm going to call it the 5-point method because, as I mentioned on the parent function, I look at those 5 points between 0 and 2 pi, being 0, pi halves, pi, 3 pi halves, and 2 pi. And what I can do is this is a very basic way to graph a sinusoid. Remember when we first learned how to graph anything, we always created a table of values. And this is basically a way of creating a table of values that you can use whenever you need to. So what you're going to do is you're going to look at the bx plus c or minus c, whatever it might be. And we're going to let that piece of the function equal these 5 values. And those are going to be our new x values that we're going to put into our table. We're going to plug those x values into the function to get y values. And we're just going to plot those 5 points, connect the dots. So let's see what that means for this particular graph right here. So we've got 2x minus pi halves. That's my bx plus c piece. All right, so I'm going to do that. I'm going to say, okay, 2x minus pi halves equals 0. So that was my first statement here, right? Let it equal to 0. This is bx minus c. So in my x, y table, if I'm going to do a table here, when I add pi halves and divide by 2, I get pi fourths. So then I want to do this. I want to go 2x minus pi halves equals to pi halves. So if I add pi halves plus pi halves is 2 pi halves, which is just pi, divided by 2 is pi halves. Now I'm not going to show all the work here. I think you guys can figure this out. And if I do 2x minus pi halves equals to pi, if I add pi halves, I get a total of 3 pi halves. Divided by 2 is 3 pi fourths. All right. Now, this isn't my favorite method to use, but it's something we can always fall back to if we don't understand the next method that will be coming up. Oops, just pi halves equals to 3 pi halves. So if I take 3 pi halves and add pi halves, I get 4 pi halves, which is 2 pi, divided by 2, which is pi. And then lastly, I say 2x minus pi halves is equal to 2 pi. And if I add pi halves, I get 5 pi halves divided by 2 is 5 pi fourths. And you'll notice that these are actually symmetrical. They're the same distance between each point here. Each point is now 1/4 pi away. Now if we plug in pi fourths times 2 is pi halves, minus pi halves is 0. Well, that's super nice because it has to do with this 0 here. So sine of 0 is 0. I plug in pi halves times 2 is pi, minus pi halves is pi halves, and the sine of pi halves is 1. If you continued this process here, plug these other 3 values in, you'll see that you'll get 0, -1, and 0. So then you go to your graph, and I need to go from 1 pi fourths to 5 pi fourths. So I'm just going to go by pi fourths. 1, 2, 3, 4, and 5. So each of my dashes is worth pi fourths. I need to go up to 1 and down to -1. So then pi fourths is at 0. My next value is at 1, back to 0, and back to -1, and back to 0 again. And we get a very nice simple graph that looks like this. Now, I didn't mention any of the other stuff that we talked about. So, by the way, this is 5 pi fourths, in case you didn't hear me say that. Notice that the period is 2 pi over 2, which is just pi. And the distance from pi fourths to 5 pi fourths is 4 pi fourths, which is pi. You'll notice that the amplitude is 1. It goes up 1 in this direction, and it goes down 1 in this direction. Right? So this is the amplitude, and actually twice the amplitude is the total height of the graph. And notice here that it phase shift, normally starting at 0, 0, it phase shift pi fourths to the right, and guess what? C divided by B is pi halves divided by 2, which is pi fourths. So notice it phase shift pi fourths to the right because of the minus sign. All right, so this is the 5-point method. It's the only one I'm going to show as using this particular method. I'm going to go now to what I think my favorite set of graphing is. It's just using the transformations. So after you find the period, the amplitude, and the center line, if it moves up or down, we're going to use our properties of transformations to find the first point. Like that last one, it was 0 or pi fourths comma 0. We know that sine starts at 0, 0 normally. The parent function starts at 0, 0. So any transformations is going to transform that point first. And then what I do is I use the period to find the ending coordinate, ending of one period, I mean. Then I break that period, the start to the end, into 4 equal parts. So basically I cut it in half and cut those halves in halves, and I use what I know about sine to graph those final 3 points. We know halfway, it's also at the 0. So at the beginning, the middle, and the end, it all is on the center line. And then the first quarter is normally up, and the third quarter is normally down. Obviously, that changes if you have a negative sine function, because then it would go down and then up. All right, I know that's a lot to swallow here, so let's look at a couple examples on how to do this. The reason I actually prefer this method, also using transformations, is it's a lot faster. You don't have to do any extra calculations. All you have to do is use some symmetry and what we know about transformations to graph an entire function without a lot of difficulty once you get the hang of it. So we're going to try this one right here. And I'm going to do a few things first. I know my amplitude is 2 because that's the number in front. So that means I go up 2 and down 2 from center. And I know the center line to be y equals 1 because it goes up 1 unit with that plus 1. My period is 2 pi over b, and b is 1. So my period is 2 pi. Well, that's kind of nice. And my phase shift is pi over 1, so it's pi units, and since it's a minus, it's pi units to the right. So here's what I need to do. I need to graph one period. So I know that at y equals 1, that's my new center line. Very hard to draw horizontal lines on this thing. All right, there's y equals 1. I call this a center line. The dashed line means nothing other than helping me center my graph. Then I know my amplitude is 2, which means I need to go up 2 from my center line. I need to go down 2 from my center line, which actually tells me my range is from -1 to 3. All right, let's put some dashes down here. We don't know what these dashes mean yet because we don't know any of the points yet. So I know I need to go pi units to the right. So if I was to since the period is 2 pi, I'm just going to say each dash is worth pi halves. And you'll get to hang of doing this a little bit more. So let's call this pi. So that means this is 2 pi and this is 3 pi. So I need to go pi units to the right. And normally I start at 0, 0, but I've gone up 1 and pi units to the right. So my new 0, 0 is the point pi, comma 1. And you would also find this out using the 5-point method if you so chose. Now, the period of this function is 2 pi, which means 2 pi away, which is down here at 3 pi. Period is 2 pi. That means it's also going to be on the center line. And like I said on the last slide, the halfway point is also on the center line. And the first quarter normally goes up, and it does go up because it's not negative here. So it's going to go up to 3, up to my amplitude. And then the third quarter is going to go down to the opposite of my amplitude. And I have 5 points. Notice it's still kind of a 5-point method, but it's using more symmetry and transformations than calculations. And there we have one full period of our function, f of x. And if you wanted to, you can continue this in the other direction. I would go down, center, and up. Here I would be up, and I can create 2 full periods, which you'll notice that the textbook actually wants you to draw 2 full periods more than anything. But I always like you guys to be comfortable with 1 period before you move on to trying to graphing 2 periods here. All right, let's try another one here. We're going to try a couple and just kind of go with it here. Okay, so 0.5 sine of 0.5x. So again, I need to figure out my amplitude, which is 0.5. I need to figure out my period, which is 2 pi over b. In this case, it's half. And 2 divided by a half is actually 4. So we get a period of 4 pi. This is actually stretching me horizontally, or stretching the graph horizontally. There's no phase shift and no vertical shift. So in this case, we don't have a whole lot to deal with in those extra transformations. Okay, so since there's no phase shift and there's no vertical shift, I know I start at 0, 0. It's actually kind of nice when you get to start at 0, 0 because I know way out here is 4 pi. And I know that's the full period, so it's going to start again on the center line. Now to use a little bit other stuff. So halfway is going to be 2 pi, and halfway again is going to be pi, and my third quarter here is going to be 3 pi. My amplitude is 1/2, so I'm just going to put this as 0.5. And my other amplitude is negative 0.5, and I'm going to go middle is going to be my center line again, and since it's not negative, it's going to go up and down, and I get to connect my 5 dots as best as I possibly can. Again, like I said, I'm better on pencil than I am on this. All right, and there you go. That's actually your function. Once you get the hang of this, you guys should be able to graph these things this quickly using symmetry and transformations. I think I have one more for us before we continue, or before I let you guys go from this particular lesson. So let's try this one here. My amplitude is 5. I'm going to put up here that it's flipped over. It's flipped because it's a negative 5, but my amplitude is still 5. So I'm going to be going up 5 and down 5 from my center line. My center line is y equals negative 5 because it goes down 5 units. And there's a very particular reason I chose this equation. Notice that pi is my b. So my period is 2 pi over pi, which is just 2. And this confuses people because there's no more pi in my period. But that just means I don't have to use pi on my x-axis. So notice that there's no phase shift, so I get to start at 0. Oh, I don't get to start at 0, 0. Sorry, I forgot to put in my horizontal or my vertical shift here. Forgot to put in my center line. This is at negative 5 here. And that means for my amplitude, I need to go up to 0 and down to negative 10. All right, so now I get to start at my new 0, 0. And out here, I'm going to say 2 because I know one period is 2 units away. So I get to be on my center line. Halfway, I'm on the center line. And then halfway again, I would normally be up, but because it's negative, I'm going to start down. And then my third quarter is where I'm going to be up, and notice my amplitude of 5 up and 5 down from center line. So now I get to connect my dots. Keep missing dots, like so. And there we go. Those 3 examples, I think I did them just as fast as I did the one example in the 5-point method. I want you to choose one and kind of stick with it and become comfortable with it. And I hope eventually you'll get to this transformation version. All right, I hope you guys learned a lot today. I think you did. I will see you guys later. I am going to be posting the cosine video up right after this. It should be shorter because it follows the sine function almost identically. All right, I'll see you guys tomorrow.